Hello everybody. In this video we will be covering one of the sections in chapter 3 of our textbook entitled Matter and Energy. In this video we're going to go over the section in chapter 3 about energy. So energy is this thing that we've managed to observe that has neither mass nor volume. Okay? So if you think about this definition of energy, basically what we're saying is that energy is all of the stuff that isn't matter. Energy has the capacity to do work, where here we are taking a very narrow definition of what exactly work is. Work means that it has the ability to apply a force over a distance. Okay, so it can move things over some kind of distance. Even though chemistry is the study of matter, matter is affected by energy, therefore energy also falls under the purview of chemistry. It can cause physical or chemical changes in matter. Just like we had a law of conservation of mass for matter, we have a law of conservation of energy, and energy can neither be created nor destroyed. The total amount of energy in the universe is constant, and there is no process that can increase or decrease that amount. So if you think back to the Big Bang, at that point, an incredible amount of energy was released, and that energy has just been changing form ever since and spreading out throughout our universe. As I alluded to, we can transfer energy from one place in the universe to another, and we can change what kind of form the energy takes on. So matter actually possesses energy. Okay, when a piece of matter possesses energy, it can give some of it to another object. So energy can be passed from one form of matter to another. All chemical and physical changes result in matter releasing or absorbing energy. That's why they're undergoing the changes, in order to release or absorb some energy. Let's talk about some kinds of energy. The first one we're going to talk about is kinetic energy. This is the energy of motion, or energy that is being transferred from one object to another. Okay, so a good example of this is like one of these hydro plants, right? The water wants to fall down and reach a lower level here, right? And in that process, it will turn a turbine, which will then create electrical energy. Potential energy is energy that is stored. So there's energy stored in this water simply by the fact that it is at a higher level than this lower water down here. There's some other forms of energy. There's electrical energy. This is actually a kind of form of kinetic energy associated with the flow of electrical charge. Okay, so we're going to learn later that there are subatomic particles called electrons, and they flow, they have a movement. Their kinetic energy is what we call electrical energy. There's heat or thermal energy. This is kinetic energy associated with molecular motion. Okay, so when molecules are made to move faster, we perceive that as an increase in thermal energy. Light or radiant energy, this is kinetic energy associated with energy transitions within an atom. All right, these are even smaller subatomic particles called photons, and they're going to move with certain kinetic energy that we perceive as light. And then there's nuclear energy. This is potential energy stored in the nucleus of an atom. This is exactly what you're thinking of, like nuclear power plants and stuff. We actually get that energy by splitting atoms. In some unfortunate turn of events, we've even used it to create bombs that can release incredible amount of energy from the nucleus of atoms. And then there's chemical energy. This is potential energy in the attachment of atoms or because of their position. Okay, so this is energy that can be released from a chemical by making or breaking of chemical bonds. We use energy to accomplish all kinds of processes, but according to the law of conservation energy, we don't really use it up. Okay? When we use energy, we are changing it from one form to another. An example here is converting the chemical energy in gasoline to make the mechanical energy to make your car move. Okay? We are releasing energy from the gasoline, and we are changing it into mechanical energy that we then use to push the car down the road. If a process is 100% efficient, we could theoretically get all the energy transferred into a useful form. The problem is that no process is actually 100% efficient. The energy lost in the process is energy transformed into a form that we cannot use. Okay, so we're not actually destroying energy, but we have some energy that was released in a form that wasn't useful to us in that process. For instance, most of the energy that we lose in a combustion of gasoline is transformed into either sound or, in particular, heat energy that escapes into the air. So your car engine is going to get really hot, and all of that energy that's released as a form of heat is lost energy. So now that we've talked a bit about energy and what exactly it is, let's talk about the units of energy. The first one we'll introduce is the calorie. And this is the amount of energy needed to raise 1 gram of water by 1 degree Celsius. You'll notice that a lot of times when we're going to define things in chemistry, we kind of base it around the properties of water. That is because water is very ubiquitous. It's everywhere. It's something that's very important to us. And it's something that, because we've been studying it for so long, we really kind of understand it pretty well. So we have a good definition there. The next unit that is very unfortunate is the big C calorie. Okay, as you can see, the only difference between these two and the way that they're written is one is written with a lowercase c and one is written with a capital C. And this unit is equal to 1,000 little c calories. So 1 big C cal is equal to 1,000 little c cals, or 1 kilocal. This is often also referred to as a food calorie, because this is the type of unit that you see on like the nutritional labels. And that's really where it came from. They were originally going to use little c calories, but then they were like, well, these numbers seem really big and kind of off-putting and stuff. So they just kind of invented this other unfortunate, confusing unit to put on the nutritional facts and make the numbers artificially smaller. The next unit is the joule, and this has a definition that's really rooted in physics. It's equal to the amount of work done when a force of 1 Newton displaces a mass through a distance of 1 meter in the direction of the force applied. And this is actually the standard SI unit for energy. So just like grams or liters, most of the world, when they're talking about energy, they're talking about joules. The next one that you would often see in some situations would be like the kilowatt hour. You're going to see this unit on, say, like your electrical bill. And it is the energy delivered by 1,000 watts of power over 1 hour. Okay. And typically we use this when we're dealing with really large amounts of energy, where these numbers using these smaller units would get really, really big and maybe difficult to print out or really conceptualize. We start moving to these kilowatt hours. So let's talk about converting between these units. Just like when we did other conversions, we just need to start with a set of facts that will be convenient for us to make conversion factors. So the first one we'll do is that 1 calorie, little c calorie, is equal to 4.184 joules. Again, 1 big C calorie is equal to 1,000 little c calories, which means that 1 big C calorie would be 4,184 joules. 1 kilowatt hour is equal to 3.6 times 10 to the 6 joules. You can see that these units are really quite a bit smaller than this, right? You need 3 million joules to equal 1 kilowatt hour. And 1 kilowatt hour is also equal to 860.421 big C calories, which would mean that it would be equal to 860,421 little C calories, because we'd have to multiply by 1,000. Let's try an example problem. A candy bar contains 225 big C calories of nutritional energy. How many joules does it contain? So when we're doing our problems, the first thing we want to identify is what is the information that we have, okay? And in this problem, we were given one quantity to work with, okay? And it was specifically was 225 big C calories. Next thing we want to ask ourselves is, what is it that we're looking for? What are we trying to figure out given this information, okay? And in this case, we want to know some amount of joules that is equal to this 225 calories. The next thing we need to do is we need to collect our conversion factors. We need to have the statements that we can use to write our ratios in order to convert to joules up here. Okay, so in this case, I'm going to show you guys how to do it using these two statements. You could build some others, but we have that 1,000 little C calories is equal to 1 big C calorie, and that 4.184 joules is equal to 1 little C calorie. Next thing that's useful is to kind of build out a map, like a little picture of what the steps are that we're going to do. So we start off with big C calories because that's what we were given. We're then going to convert that to little C calories, okay, because that's the statement that we have. We can relate the big C calories to the little C calories because we don't have any big C calories in this statement. And then once we're in little C calories, we're going to convert over to our final answer, which is going to be in joules. Now we've drawn these arrows to kind of indicate an action that we're going to take. So what we want to do is we want to associate each one of these arrows with the action that we're going to do. Okay, so then the first one, we're going to use a conversion factor that looks like this. Okay, we have 1,000 little C calories per every 1 big C calorie. We're putting the unit that we want to get rid of in the denominator. We're putting the unit that we want to wind up at, the little C calories, in the numerator. For this one, our conversion factor is going to be 4.184 joules per every 1 little C calorie. Again, we're now in little C calories, right? Because after we've applied this, that's the unit we're going to be in, okay? And so we need to get rid of the little C calories, and we need to go to the joules, and we have all that same convention where the unit we want to get rid of is in the denominator, and the unit we want is going to be in the numerator. Putting this information together, we wind up with a mathematical statement that looks like this. We start with our given quantity, we apply our first conversion factor, we can now cancel the big C calories. We are now in little C calories, and then in our next step we can cancel the little C calories, and we wind up having units of joules in the end. When we pump this all in the calculator, we're going to take 225 times 1,000 times 4.184. You could divide by 1 here in these scenarios too, but obviously dividing by 1 isn't going to change it, so mathematically it would be this times this times this. And we wind up with this raw value here, okay, 941,400 joules. And you notice that what we're doing here is we're highlighting the 1 here because that's our last significant digit, right? Because here we're limited to 3 because we were only given 3 sig figs in this initial given quantity. So now we need to round to that value. And if we want, we can also express this, because it's a fairly large number in scientific notation, and we wind up with 9.41 times 10 to the fifth joules. The last thing that you always want to do whenever you're going to do a problem is make sure that you check the solution. Check to make sure that it makes sense in the end. Okay? So in the end, we're making the statement that 225 big C calories is equal to 941 times 10 to the fifth joules. All right? This magnitude of the answer makes sense because the joules are much smaller than the calories, right? So what we needed to make sure of here, a little C calorie is bigger than a joule, right? A big C calorie is bigger than a little C calorie. This number ultimately needed to be larger than this number. If we had gotten a smaller number than 225, we know we would have made a mistake somewhere along the way when we were making these conversions. So now we're going to switch gears here a little bit, and we're going to talk about the meaning of heat. Heat is the exchange of thermal energy between samples of matter. It's kind of a different sort of idea than what we actually perceive heat as being, but heat is actually the process of thermal energy moving from one sample of matter to another sample of matter. Heat flows from the matter that has high thermal energy, which we would perceive as something being hot, to matter that has low thermal energy. Okay, and that kind of makes sense. If I heat up one end of a metal rod, the heat is going to flow through the metal rod to the colder end. Okay, it never goes the other way, right? You never have a scenario where all of a sudden the rod just spontaneously gets hot on one end and cold on the other. Okay, it's always going to spread out till it's able to equalize itself as best it can. And that process will always happen until they reach the same temperature. At that point, heat's not going to flow anymore because there's no place really for it to flow to that it would prefer over any other place. This process happens through molecular collisions, okay? And we don't really always think about it that way either, okay? Really what's happening is the molecules, when they have a lot of thermal energy, they start vibrating or moving more rapidly. They start bumping into each other, and they start giving more energy to the ones next to each other until that all equals out. So it's actually through the collision of molecules and atoms that heat is able to be transferred. It's also important to note in this that there is no such thing as cold, really. Cold is just the absence of thermal energy, okay? There is nothing that actually travels or that is moving that causes cold, if that makes any sense. So let's talk a little bit about the meaning of temperature. And this is so important in our lives, yet a lot of times we really don't think about really what it is. So temperature is a measure of the average kinetic energy of the molecules in a sample, which is very different than how we perceive temperature in our everyday lives. But the temperature that we experience actually has to do with how fast the molecules around us are moving. Not all of the molecules in any particular sample have the same amount of kinetic energy, but we can talk about the average kinetic energy that they have, okay? A higher temperature means a larger average kinetic energy. So when we heat up a room, what we've actually done is take the air molecules in the room and given them more energy. They are now moving and bouncing around the room faster than they were before, and we perceive that as the room getting warmer. So let's talk about some of our temperature scales now. We'll start with Fahrenheit. So this is the temperature scale that we're most used to in America. And it was based by a guy named Fahrenheit on two reference points, okay? The freezing point of concentrated salt water, so the water from the ocean where he was living, was 0 degrees Fahrenheit, and the average body temperature, which he reckoned was about 100 degrees Fahrenheit. We now know that he actually didn't make either of these measurements super accurately, but you can see that there is some usefulness to this as a temperature scale to measure the weather. Okay, at anything lower than 0 degrees Fahrenheit, we no longer can melt ice with salt, which can create a dangerous situation where things can freeze up and there's not much that we can do about it. And you are certainly in risk for hypothermia if it's anything lower than 0. And if the temperature outside goes above your body temperature, then you will have a lot of trouble regulating your body temperature, and only a couple degrees higher than 100 degrees Fahrenheit, and you are at risk for heat stroke. So being between 0 and 100 is pretty much where we can reasonably sustain ourselves with, the typical equipment if we're exposed to those temperatures. So now we know that a more accurate measure of how the average body temperature is at 98.6 degrees Fahrenheit. This places our room temperature around 75 degrees Fahrenheit. And so now we'll move on to Celsius. The Celsius temperature scale is used as its two reference points, the freezing point of distilled water. Okay, so again, we're coming back to water as our reference here at 0 degrees Celsius, and the boiling point of distilled water at 100 degrees Celsius. So again, we understand water very well. It's important to us, and we want to use that as our reference for this. And we can get really pure water because we've been trying to purify water for a long time. Distilling it typically is going to produce some pretty pure water. So we could measure this really effectively. It led to more reproducible standards. And this is the one that's most commonly used in science. You're typically going to see scientists use the Celsius scale. And under the Celsius scale, our room temperature is about 25 degrees Celsius. So let's talk about Fahrenheit versus Celsius. A Celsius degree, and this is really key to kind of understanding this, is 1.8 times larger than a Fahrenheit degree. Okay, so every time we go up our Fahrenheit scale 1.8 degrees, almost 2 degrees, that's only 1 Celsius degree. Okay, so you're going to see the numbers climb as it got hotter in Celsius, much or almost half as fast as you would in the Fahrenheit system. The standard used for 0 degrees on the Fahrenheit scale is a lower temperature than the standard used for 0 degrees on the Celsius scale, right? Because he's talking about when salt water will freeze, and we know that that's a lower temperature than when distilled water will freeze. Okay, so they don't even line up with each other. And using this information, we actually can derive a formula to interconvert between them. Okay, so the temperature in degrees Celsius is going to equal the temperature in degrees Fahrenheit minus 32. This 32 is coming from where the 0 is on the Fahrenheit scale. Okay, 0 degrees Celsius is 32 degrees Fahrenheit. All right. Divided by 1.8, which has to do with the difference in size between a Celsius degree and a Fahrenheit degree. If we use algebra to reverse this, okay, solving for the temperature in Fahrenheit, we would arrive at this equation here, where the temperature in degrees Fahrenheit is equal to 1.8 times the temperature in degrees Celsius plus 32. So now I'm going to introduce a new temperature scale that you may have never heard about before, called the Kelvin temperature scale. You might have noticed that both the Celsius and Fahrenheit scales have negative numbers. They allow for there to be objects that are colder than 0 degrees Celsius or colder than 0 degrees Fahrenheit, and therefore have to have negative values. The Kelvin scale is an absolute scale, meaning it does not allow for negative values. 0 Kelvin, and notice we don't actually use the degree notation here. It says 0 Kelvin, is called absolute zero. It's the lowest possible temperature, period. At 0 Kelvin, all molecular motion would stop. And so therefore it's theorized that you could never actually get all the way to 0 Kelvin, but we've come very, very close. Absolute zero is a theoretical value obtained by following patterns mathematically. There was a scientist by the name of Kelvin. He was doing some experiments with gases. He was able to relate their pressure and volume to the temperature, and by doing some very careful measurements, he was able to extrapolate, looking at his data, and determine what the coldest temperature possible for those gases would be. So let's talk about the difference between the Kelvin and the Celsius scales. The size of a degree on the Kelvin scale is the same as on the Celsius scale. So 1 Kelvin is the same as 1 degree Celsius. And again, we do not actually say degrees, we just call them kelvins. So just as the Celsius, a degree Celsius is 1.8 times larger than 1 degree Fahrenheit, so is 1 Kelvin. The zero standard on the Kelvin scale is much lower than on the Celsius scale, though. And specifically, it's 273 degrees lower. Okay, so 0 degrees Celsius is 273 degrees Kelvin. 0 Kelvin is negative 273 degrees Celsius. To interconvert between them, we have this formula here. Okay, so to get 2 Kelvin from degrees Celsius, you're going to add 273 degrees. To get 2 degrees Celsius from Kelvin, you would subtract 273 degrees if we're reversing this equation. If we take a look at the temperature scales next to each other, we also have some values here that kind of give us some sense of how cold things are. Okay, so 100 degrees Celsius is here. This is the boiling point of water. On the Kelvin scale, we'll add that 273, so it would be 373 degrees Kelvin. It's 212 degrees Fahrenheit. And I'll even introduce this other scale here that we're not really going to talk much about, but it's called Rankine. And what the Rankine is it's the Fahrenheit equivalent to the Kelvin scale, where 0 Rankine is absolute zero, and each degree is the same as the size of a Fahrenheit degree. And so boiling point here is going to be 671 Rankine. You typically only see Rankine really pop up some engineering texts and stuff. Sometimes they use this Rankine scale instead. Regular temperature of a room would be 25 degrees Celsius, but it's 298 Kelvin. This is also known as the standard temperature, we will see later. It would be 77 degrees Fahrenheit and 557 degrees Rankine. Now, if we look at, say, the difference between 0 degrees Celsius and 270 degrees Kelvin, we can see where we're getting that value from. That every Kelvin number is just 270 degrees higher. To reinforce the idea of the size of the degree, I want to take a look at this. So between 0 and 25 degrees Celsius is 25 degrees, right? And also between 273 Kelvin and 298 Kelvin is also 25 degrees, okay? Whereas on the Fahrenheit scale, between 32 and 77, we've got 45 degrees there, right? So that's almost double that 25 degrees that we see there. And over here on the Rankine, between 492 and 337, we also have 45 degrees of difference. So these are the same size, whereas over here these are different size, and you can tell by looking at the difference between any 2 points. Down here we can see things like this is where ice would melt, this is where liquid mercury would melt, so we can actually freeze mercury at really coldish temperatures to make a solid. Down here is the boiling point of oxygen, right? So this is where we would have liquid oxygen. It's down here, which you may have seen before if you ever do like medical grade tanks and stuff like that. There's some liquid oxygen in there sometimes. And then we get down into the really, really cold stuff, and how cold we've actually managed to get to. The coldest material we've ever made is liquid helium. It has a boiling point somewhere around 4 Kelvin, so just a little bit warmer than that absolute zero. And only in some very fancy lab cases have we ever pushed that any colder than that. So let's talk about how we're going to do an example problem about converting between Fahrenheit and Kelvin. So we're going to be asked the question, let's convert 310 Kelvin to Fahrenheit. First thing again, we're going to ask ourselves is, what are we given? What is the information that we have? What are our quantities here? The only quantity we have is this 310 Kelvin. The next question is, what is it that we want to find? We want to find what is this equivalent in degrees Fahrenheit. And we know that this is going to be a conversion problem. We're converting between 2 scales here. We'll collect our equations that we can use. In this case, I'm choosing to first convert the Kelvin to degrees Celsius. And then we'll use this equation here to convert to degrees Fahrenheit. But we're going to have to invert these. Okay, so we're going to have an equation that is degrees Celsius. That's going to output degrees Celsius. We're going to have an equation that's going to output degrees Fahrenheit. Okay, I don't want you guys to sway you. If you have an equation like this, you can do a little algebra to figure that out. Let's talk about what our solution map is going to look like. We're going to start off with Kelvin, because that's what our given is. We're going to perform an action, a conversion. We're going to wind up in degrees Celsius. We're going to perform another conversion, and we'll wind up in degrees Fahrenheit. To go from Kelvin to degrees Celsius, we start with our known equation here, and then we invert it to get an equation for degrees Celsius, the quantity that we want out. To go from Celsius to Fahrenheit, we start with our known equation, and then we can invert it to get a equation for degrees Fahrenheit. So I showed you the little intermediate of the algebra right there. So now it's time to apply our solution map. We'll start with our equation for degrees Celsius from Kelvin. We're going to plug our known Kelvin value in here for K. We'll crank that out and we'll see that 310 Kelvin is 37 degrees Celsius. Then we'll come back to our equation for degrees Fahrenheit. We're going to take the output of this first equation, our degrees Celsius, and we're going to plug it in here. Then we'll perform this multiplication and add the 32. And we see that we get 98.6 degrees Fahrenheit. When we round to our sig figs, we get 99 degrees Fahrenheit. Because we had ended with a 0 here that's ambiguous, we'll take this to be 2 sig figs. Now let's check our solution. We're making the claim here that 310 Kelvin is equal to 99 degrees Fahrenheit. We know that we have the right units because we wanted degrees Fahrenheit. That's what the question asked. And the magnitude of the answer makes sense since both are above but close to room temperature, right? So we knew 298 was room temperature and that was 75 degrees Fahrenheit. So we know that we are in the ballpark here for these temperatures. Now let's talk a little bit more and bring it together how energy and temperature are related. So the temperature of an object increases depends on the amount of heat that is added, okay? So that's a pretty simple intuitive statement, but we're actually going to put some math to it. And when we do that, we're going to talk about a quantity that is heat, and we're going to use this lowercase q here to represent that quantity. And so let's think about how this works. So if you double the added heat energy, the temperature will increase twice as much. That makes sense. The amount the temperature of an object increases depends on its mass. That also makes sense, right? If I have a small rock, I add a certain amount of heat, it's going to get real hot. If I had a big rock and I added the same amount of heat, it's not going to get as hot. This is also a linear relationship. So if you double the mass, it's going to take twice as much heat to raise the temperature of the same amount. Okay? So using those facts, we also still have to take into account the heat capacity before we can really get a quantitative way of calculating this. And what heat capacity is the amount of heat a substance must absorb to raise its temperature 1 degree Celsius. So this is implicit to a material. And if you think about it, this is also pretty intuitive, okay? If I take and put a gallon of milk in the fridge, it is not going to cool down as fast as if I added, say, some aluminum foil in there, right? If you put glass into the oven, it's going to take longer for that to heat up than a metal container. So there's something intrinsic to the material that changes the amount of heat you have to add to raise its temperature. Some things want to raise their temperature very readily. Some things resist it. The units of heat capacity are going to be calories per degree of some sort. Okay, so the energy we're putting in per the amount of heat, that temperature that it rises. All right. So if we think about this, right, if we have to put in a small amount of energy in order to get it to rise 1 degree Celsius, say, then that would mean that we have a small number in the numerator versus the denominator here, and we're going to have a low value. So metals, for instance, have low heat capacities, and insulators, things that resist change in temperature, like the gloves that you use to handle the hot pans when they come out of the oven, are going to have high ones. Okay, we're going to have to put a lot of energy. We're going to have a large numerator in order to raise them 1 degree Celsius, but we're going to have a low one for the metals. Specific heat, okay, takes into account the amount of mass that we have. So this is the heat capacity of 1 gram of the substance. It's going to have units of energy per gram per degree Celsius. And this is the first time that we're really using these a little bit more complicated derived units, but I don't want them to sway you, and I want you to understand exactly what this means. So this is calories divided by grams times degrees Celsius. Both the grams and the degrees Celsius are in the denominator of this unit, meaning that if we multiply by grams and multiply by degrees Celsius, we're going to get out calories. The specific heat of water is 4.184 joules per gram degree Celsius when it's in its liquid state. Okay, that would be the equivalent of 1 calorie per gram per degree Celsius. This is due to the way that we define the calorie. All right. And it's going to be a little less when they're in other phases like ice or steam. So the specific heat is the total amount of energy required to raise the temperature of 1 gram of the substance by 1 Celsius degree. The larger a material's specific heat is, the more energy it takes to raise its temperature to a given amount. Like density, specific heat is a property of the type of matter. Okay, it's specific to that matter. It doesn't matter how much of the material that you have. All right, we've made it independent of the mass by basically by dividing by the mass here, and it can be used to identify the type of matter. Okay, if I have a pure substance, I can identify it based on its specific heat. Water's high specific heat is such a good cooling agent. It's why we use it when we sweat, for instance. Okay, it's going to take a lot of energy from your body in order to get it to vaporize. Here's a list of specific heat capacities for various different compounds, pure substances. You can see ones like metals like aluminum and stuff have pretty low specific heats in relative to water. And that in general, they're usually pretty much lower than water. Water has a really high specific heat capacity, and you can see that that's really only true for liquid water. Solid water and gaseous water, it's almost halved. Okay. Now we can bring all of our observations together, and hopefully it'll make a little bit more sense, the equation that we have that's going to relate the heat and the temperature and mass. So we know from our observations that the amount of energy gained or lost by an object depends on 3 factors: how much material there is, what that material is, and how much the temperature changed. So our equation becomes the amount of heat is equal to the mass, how much material there is, times the heat capacity, that's specific to what the material is, times the temperature change. And we're going to represent that like this. So you're going to see Q is equal to M for mass, Q being the heat, M for mass, C is the heat capacity, and this delta T is a single term. Delta means change in temperature. And then we're going to multiply them together. You may see this written just with an M, with a C next to it, with the delta T next to it, where we're then implying that we're going to multiply them all together. So don't let that sway you either. Okay, let's go through an example equation where we're going to use our new equation, or an example problem where we're going to use our new equation to calculate some heat energy. So let's take a look at this problem. This one is a little bit more complex than any one we've handled so far, but we're going to use our process to break it down, and we'll see that it's really not too bad. So gallium is a solid metal at room temperature, but it melts at 29.9 degrees Celsius. If you hold gallium in your hand, it melts from your body heat. How much heat must 2.5 grams of gallium absorb from your hand to raise its temperature from 25 degrees Celsius, so room temperature, to the 29.9 degrees Celsius when its melting point? And we're given an extra bit of information here that we're going to need to solve it. We're given the specific heat capacity of gallium is 0.372 joules per gram degrees Celsius. So we're given more information, more quantities in this than we have in the other problems. Let's make a list to make sure that we don't miss any. So we're given the mass of gallium, 2.5 grams. We're giving a starting temperature, 25 degrees Celsius. We're given a final temperature, 29.9 degrees Celsius. And we're given the specific heat of gallium, 0.372 joules per gram degrees Celsius here. It's useful to make sure that we define these, put them onto your paper using the variables that are going to appear in our equation. So our mass is little m, our specific heat capacity, we're going to use C, and we can make sure to use a subscript I here to show that this is the initial temperature, the temperature we started at, and the subscripted F here to indicate that this is our final temperature, the temperature that we eventually arrive at. Now let's ask ourselves, what is it that we want to find? Okay, and we're being asked for the amount of heat in joules, which in our equation was the Q, right? And so we are already solved for that variable, so we can apply this equation directly now. Let's write our solution map. We are going to plug in all of these variables that we have collected up here. We're going to perform some mathematical action, and we're going to get our Q value out. We're going to do that using this equation. Now, when we plug those values in, we do have to be careful in particular about one thing. This delta T is the change in temperature, okay? You should never be plugging in just one of the temperatures. You want to know how much the temperature changed, and you're going to do that by doing a subtraction. So as we've discussed, it may be true that one of these values are negative, and so you're going to have to be able to deal with negative numbers in this subtraction. And it may be true that the final temperature is not higher than the initial temperature, that the thing cooled down, and that this overall term will be negative and make Q negative. These are all possibilities for this delta T term here, okay? There is also a very important convention that we need to be aware of, and that is that we always take the final temperature minus the initial temperature. Okay, it's always going to be that way. So do not get yourself confused and reverse these. Okay. The first thing that's convenient to do is to do that subtraction and get your total value here, and then tell yourself, does that make sense? Okay. If I know that this gallium went up in temperature from 25 degrees Celsius to 29.9 degrees Celsius, does it seem like 4.9 seems reasonable for that increase? It sure does, right? It should also be positive because the temperature went up. This term would be negative had the temperature gone down, okay? The positive or negative implies a sense of direction in this case. Is it cooling or is it heating? Next, we're just going to do these multiply 2.5 times 0.372 times 4.9. If we look at our units here, we're going to cancel these grams, and we're going to cancel this degrees Celsius here, okay? Because this guy's in the numerator, and these guys are both in this guy's in the denominator, and these guys are both in the numerators here. It's almost as if there's an applied over 1 here, right? So we cancel those. We're going to wind up in joules. We can run out a few decimal places and then highlight the one where we need to round, okay? So that is the number. The 5 there is going to dictate where we need to round to, because we only get 2 sig figs from this, and our final answer is going to be 4.6 joules. Now let's check our solution. So we said that Q is equal to 4.6 joules. We got the right units. We wanted joules, okay? The magnitude of the answer makes sense since the temperature change, mass, and specific heat are all small, right? We don't have a whole lot of gallium. We're not raising its temperature a lot, and gallium has a fairly small value, less than 1 here, where we know water, for instance, would be at a 4. This is almost 1/10 of the specific heat of water.